All of your life, you have only dealt with temperature for how hot or cold something is, but there's something more that has to be discussed because items can be at the exact same temperature, yet have very different effects on you if you end up touching them, because they hold different amounts of thermal energy. Thermal energy is the sum of the kinetic energy of a group of particles. Now, temperature's definition is the average kinetic energy of a group of particles. So notice the difference. Here, it's all of the kinetic energy added up. Now, heat is another term you use quite often. It's the movement of thermal energy. So make sure you don't use the term heat unless we're talking about thermal energy moving from one object to another. Now, each item actually holds a different amount of thermal energy depending upon its specific heat capacity. Now, specific heat capacity is the heat, or the energy, that should say, required to raise 1 kilogram of a substance 1 Kelvin, where Kelvin is the temperature scale based upon absolute zero. But looking at our equation down here, Kelvin is degrees Celsius plus 273.15. In other words, change in 1 Kelvin is also going to be change in 1 degree Celsius. So those can be interchangeable for this equation specifically, not for other equations. Now, the equation for specific heat capacity, change in thermal energy equals the mass times the specific heat capacity, that's measured in joules per kilogram Kelvin, times the change in temperature. In other words, two objects, let's take aluminum and copper, for example, two metals, can have the exact same temperature. But because aluminum has a higher specific heat capacity, it will have a greater amount of thermal energy. This means aluminum actually takes longer to heat up. You would have to apply more thermal energy to get the same change in temperature to try to heat aluminum up than you would copper, and vice versa. Aluminum will hold on to, it has more thermal energy, so it actually takes longer, if you will. You have to take away more thermal energy to get it to decrease the exact same amount of, the exact same temperature amount that occurs with copper. Now, every item in our world pretty much has its own specific heat capacity, which means it is very useful. This idea is very, very useful for being able to identify the material. Because if you add a certain amount of thermal energy to it, and you know that because maybe you're using an electric heater and you're able to calculate the amount of electrical energy that you're putting in, or some other type, you can easily measure its mass. You can easily measure its change in temperature, final temperature minus initial temperature. Let me point that out. Change in temperature, final temperature minus initial temperature. That would allow you to calculate the specific heat capacity, C, and then compare against a known table of specific heat capacities to identify what type of material you have. That process is called calorimetry. You place a liquid a lot of times and with an electric heater inside of it, and you warm it up, and you're able to calculate the specific heat capacity. You can also do it with metals. Sometimes what we do with metals is we actually submerge them in water of known temperature. We heat the metal up and then submerge it in water, and we wait for the two to come into thermal equilibrium. Thermal equilibrium is where all parts of any system are at the exact same temperature. Another note here that you just need to simply remember, because it's going to be used periodically. Heat always flows from hot to cold. Thermal energy, heat, right, movement of heat. Heat is the movement of thermal energy. So heat flows from hot to cold, or thermal energy moves from hot to cold, never from cold to hot. One specific heat capacity that I want to point out is the specific heat capacity of water, 4,186 joules per kilogram Kelvin. You have to put in over 4,000 joules of energy just to get a kilogram of water, 1 little kilogram of water to heat up 1 Kelvin. By the way, it's not degrees Kelvin, it's just Kelvin. That's an insane amount of energy, especially compared to everything else. Water on our world contains, or whenever you heat it up, it holds on to so much thermal energy. That's why whenever you're trying to boil a pot of water, it takes so long. The stove has to put in a lot of energy just to bring that water up to 100 degrees Celsius. It takes a long time for the stove to be able to do that. And likewise, boiling water is actually very, very dangerous because it contains so much thermal energy. So if you spill it on yourself, it can give you incredibly bad burns. A couple of example problems now. I have a 1.5 kilogram bucket of water that we leave out in the sun, and because it's receiving radiation energy, it's receiving thermal energy through the form of radiation, that's how it's being transmitted, the water heats up from 17 degrees Celsius to 27 degrees Celsius. How much thermal energy did the water actually end up receiving? Well, that needs to be calculated using my specific heat capacity equation. Change in thermal energy equals mass times specific heat capacity times my change in temperature. So I drew a quick picture, wrote down all of my knowns, and I'm looking for delta Q, and that's just simply plug in and solve. Now, you won't have to memorize any of these specific heat capacities. They will be given to you in the form of a large table. That way you can actually pick them out. But you will have to be able to recognize, hey, I need to know the specific heat capacity of water here because that's the substance that's heating up, and then reference a table, like on the previous slide, to find out specific heat capacity of water, 4,186 joules per kilogram Kelvin, and then be able to plug that in. And you come out with two significant figures, 63,000 joules or 63 kilojoules, and an insane amount of energy has to be imparted to this water just to heat it up 10 degrees Celsius. Might I also point out, final temperature minus initial temperature. So if you're actually heating it up, you're going to have a positive number here, which will give you a positive amount of energy that it received. On the other hand, if it's cooling down, and so you had a lower number for the final temperature and a higher number for the final, you'll come out with a negative change in energy, meaning that it's giving off energy. Next is a similar but slightly different problem. We're actually going to try to identify some unknown liquid, and a common way to do that is you put a liquid into a calorimeter with an electric heater. You use the electric heater to give it a specific amount of energy that's calculated just using electrical energy, current times voltage times time, not a big deal. And whenever we do that, 9 kilojoules of energy in this problem is given to it. Kilojoules we need to make sure to convert. And it raises the temperature from negative 5 degrees Celsius up to 10 degrees Celsius. Whenever you're doing these type of experiments, it's always best to do it under cooler temperatures, just in case the liquid that you are using might be flammable. Now on this one, we can already see it's not water because it's still at liquid below the freezing point of water at negative 5 degrees Celsius. Now, we're going to once again use our thermal energy equation with specific heat, delta Q equals mc delta T, and we're going to solve for the specific heat capacity, C, of the unknown liquid, because each different substance around our planet has its own unique specific heat capacity. So if we can solve for the specific heat capacity, we can compare it against the table on the previous slide to identify what type of liquid it is. So substituting everything into my equation and making sure I convert correctly, 9.0 kilojoules, that's 9 times 10 to the third, that's what kilo means, times 10 to the third, or 1,000, so I'm going to put it in standard notation for you this time, 9,000 joules. Also, we knew our mass in grams, base unit for mass in physics is kilograms, so 0.250. And my change in temperature, final, which was 10, minus initial, negative 5, note negative times a negative, will end up giving me a positive here, and I'm going to solve for my specific heat capacity. Multiplying 0.250 times 15 gives me 3.75. And I come out with a specific heat capacity of 2,400 joules per kilogram Kelvin, which whenever you look at the table in the back is ethanol. So we've identified the material, ethanol, flammable. I'm glad we did this under cooler temperatures.